All right, welcome Cedarville University students. Like I had mentioned, I am going to do a screencast, and that's because we missed out on the very end of our light lesson. So I want to go ahead and go through the rest of the light lesson. Remember, we discovered last time we left off that light is both a particle and a wave. I showed you a video on that, and then we also looked at Dr. Quantum. Dr. Quantum was actually using electrons, and electrons were acting very similar to light particles, where the electrons are acting both as a wave and a particle. And how do we find that out? By sending light, or in this case, it was electrons, through the double slits. And they found constructive and destructive interference. If you want to, you can find that somewhere on the YouTube very easily. And just letting you know, there will be a question about a double slit experiment on your test, and I'll have something to do with light, of course. So let's go on. This is where we left off the other day, and there's a few, I don't know, probably about 10 more slides we need to go through. And one of the things that we need to talk about is when light strikes an object, there's three different things that can happen when light strikes an object. Number one, light can be transmitted or passed through the object. You can see with this arrow right here that the light is going through this substance. Let's say it's glass. And are there any surfaces where light can be 100% transmitted? I'm going to say no. There is some very good glass out there, but no matter how clean the glass is, I can't say 100% of the light's going to make it through. Maybe 99.9% or something like that. And it says light can be reflected or bounce off of an object. This is called reflection. This is shouldn't be anything too terribly new to you, but light hits something and then it bounces off. That's reflection. And then there's the last option where light can actually be absorbed. It says light can be absorbed in which energy is consumed by an object. Are there any surfaces where 100% of the light is absorbed? No, there isn't. Not that I know of. But there are some certain colors that absorb a lot of light. You might notice I've got a link up here for Vantablack. And what you can do is I'll put that live on YouTube, and you can click this link and watch a little bit about Vantablack. Basically, it's a substance that specializes in absorption. It reflects almost no light. It reflects some, but almost no light, and they call it Vantablack. It's really pretty intense stuff. So you can go ahead and pause the video, click on Vantablack. It will open up in a new window, and then you can come back to this screen here. Okay, so hopefully you've done that, and you've got this screen still up. Let's go to the next slide. Oh, and it says, can you think of a real-life example of each? Yeah, with transmission, let's say glass, reflection, mirror, absorption. Let's say the color black or something like Vantablack would work in that case. Well, let's talk about the two different types of reflection. One type of reflection is specular reflection. Look at the light waves here. They're coming down and they're hitting this surface and they're bouncing off in a straight line. You see they're not going all over the place. But then there's diffuse reflection. Diffuse reflection is when light is striking an object and then it's bouncing off in all sorts of different directions. Let me see if I can show you an example real quick with my webcam. So hold on. Well, unfortunately, I lost my laser pointer. The whole thing I wanted to do was I wanted to shine a beam of light on the whiteboard back here. And the beam of light hits the whiteboard, bounces off, and then you can see the reflection on the ceiling. Whereas, if I were to take the laser pointer and I were to shine it directly on one of those ceiling tiles, it doesn't reflect off of the ceiling tiles and then bounce down to the ground. The light hits the ceiling tile and then it's scattered all over the place. Kind of like what you see here with this diffuse reflection. The light would actually strike that and then bounce in every which direction. Why? Because this surface right here is actually a rough surface. A smooth surface, maybe you've noticed this, reflects light a lot better. A smooth surface like a mirror or something like that. Whereas this surface, which is rough and bumpy, there's diffuse reflection and the light goes all over the place. So diffuse reflection is when light strikes an object and bounces off in all directions. It typically occurs when light strikes a bumpy, rough, or unsmooth surface. So I guess those are all synonyms. And then there's specular reflection. Specular reflection is reflection when light waves bounce off of an object at an unpredictable angle. Wait a second, at a predictable angle. I'm sorry, I read that incorrectly. So it typically occurs on a flat, smooth surface like glass or still water, or maybe the whiteboard behind me. If a laser pointer hits that, it's going to bounce off and it's going to go like in a straight line. All right, keep going. Let's talk about refraction. Hopefully refraction isn't too terribly new to you. We already talked about it when we talked about waves, but it says, remember that refraction is the bending of a wave as the wave changes speed when it enters or exits a new medium. So the thing is, different substances have different indices of refraction. If you look over here on the left, we can see light is traveling at one speed, it hits the glass and slows down. And then after it slows down, it comes out of the glass again and it speeds up at its regular speed again. Here we've got another example of refraction. Light refracting through, maybe it's calcite, I don't know, maybe it's a piece of plastic, maybe it's a piece of glass, I don't know. Here's another good example of refraction. Take a look at this pencil. You see one pencil up here, but if you look closely in the glass, it appears that there's a second pencil down at the bottom. Of course, it's not two pencils. It's just refraction that the light is bent when you look through it. That should be review. Let's talk about light and color. I think most of us know this as well, but it says light is responsible for the presence of color. Without light, there is no color. For example, go into a dark room, like maybe go into your dorm room, shut off all the lights, and then tell someone what color sweatshirt they're wearing. You can't do it because you can't see color without light. You have to have light in order to see color. There is no color without light. Take a look at this prism up here. You can see the beam of light hitting this prism, and as it goes through the prism, it's bent into the different colors. So that should help us understand that white light contains, I'm sorry, that's the bell at my school. White light contains all the colors within it. So you can shine white light into this prism, and what comes out? All the different colors. Or we could reverse that, and we could shine all the different colors together, and we would get white light. So white light can be separated into all the colors of the prism, which brings me to a fun and interesting question. Look down here. It says, why do some colors look different at home? So maybe you've been to Home Depot, maybe you've been to Lowe's. You look at some of the different colors here because you're about to paint a wall, and you get some paint swatches, and you take it home, you paint it on your wall, and you're like, that's not what it'll look like at all. Why? Because you're using different light. Look at the light that they have here at Lowe's. The light that they're using is a very, very bright light. If you don't have that same kind of lighting at your house, the colors will appear different. So some of the new paint places, they actually have incandescent LED and different types of light that you can test the paint under and see if it's the color that you want. And by the way, the color black absorbs all the wavelengths of light, and it reflects no wavelengths of light. So black is not reflecting any kind of color at all. Instead, it's just absorbing light. And we'll talk about that in a second. I want you to pause the video in just a minute and watch this video that says They Might Be Giants. It's another one of those songs. I know you might be like, wow, why is Mr. Wagner showing us this? This is for kids. Well, guess what? You're going to be teaching kids, so this is a perfect resource to teach your kids about the spectrum of colors. It's the Roy G. Biv song. So pause it, watch that. Okay, great. Hopefully you're done pausing. We're back. We're watching this. Let's go to the next slide. Here's the crazy thing about color. The color of different objects is determined by the wavelength of light that the object reflects and absorbs. Here's what I mean. If you look at these bananas down here, I'm going to go ahead and tell you that these bananas are not yellow. And you're thinking to yourself, no, look, you can look at them very clearly. They are yellow. No, they're not. Instead, they are purple, they are blue, they are green, they are orange, and they are red, but they are not yellow because the bananas are reflecting the color yellow. So the color yellow hits the bananas and bounces off. So they're not yellow, it's reflecting yellow. Instead, it is absorbing green because the bananas are green. It's absorbing blue because the bananas are blue. It's absorbing purple because the bananas are purple. But one thing that the bananas are not is yellow, which I know sounds very, very confusing. Red objects absorb all the colors except for red. Take a look at this apple. Here's white light striking the apple, and what is reflected from the apple? The red frequency of light. So the red frequency of light is being reflected. So we look at the apple and we say, oh, it's red. Well, no, it's not. It's every color but red, which sounds kind of confusing. Yellow objects absorb all the colors except for yellow. What do white objects do? That's a good question. Ask yourself right now, what do white objects do? What color do they reflect? Because is white really a color? White objects reflect every color. They reflect all colors together equally. And if they reflect all colors together equally, that together makes white. To help explain this, let's pause the video again. Click the TED Ed video on how color works. You'll find it pretty interesting. So go ahead and click that now and watch that. Okay, hopefully you've watched that and you're back. But let's go to this next slide here real quick, and it's kind of a fun story. So how is light reflected and absorbed by these two different cars? I wish I had these two Corvettes. I don't. But I remember trying to get the point across once in middle school, and I told my students, I said, hey, I had two Corvettes, and I drove the white Corvette to school, and one day I walked home for lunch, and I realized I was late, so I drove the black Corvette, and I had a black Corvette and a white Corvette parked right next to each other at school. And at that point, a kid raises his hand, do you really have two Corvettes? And another kid says, teachers are pretty much rich. They make like $100 a day. So they're wrong, of course, and I don't have two Corvettes. But the question was, at the end of the day, it's been a really, really sunny day. Which Corvette should I get in and drive home? And most of the students said a white Corvette. And I said, why would I want to drive the white Corvette home and not the black Corvette? And they said, the black Corvette is hot. And I said, why is the black Corvette hot? And they said, the black Corvette absorbs light. They're correct. The black Corvette does absorb light. The black Corvette doesn't reflect the light. And since it's absorbing light, it gets hot. The white Corvette reflects all the light. And since it reflects all the light, it isn't hot. All the light is bouncing off of it. So it says white light reflects all the colors of the spectrum. The color black absorbs all the colors of the spectrum. So my white Corvette is reflecting all the light from the spectrum. The black Corvette is absorbing all the light from the spectrum. So that's how these two would be kind of different. So it says, how will the reflection and absorption of light affect the temperature of these two cars sitting in the sun all day? We just answered that. We said that the white car reflects all the wavelengths of light. The black car absorbs all the wavelengths of light. Great. And we just said what we're saying. Okay. And here's another example. Look up here. We've got a black surface. Look at that. What is it reflecting? Nothing. But we've got a white surface here. It's translucent, but it should be white. But the white surface is reflecting all the colors of light. So now we know a little bit about light. But what if we were to put the primary colors together? Let's take a look at that. When the three primary colors of light are equally mixed, they create white light. If you have one of those old-fashioned television screens, you need to get really, really close to the old-fashioned television screen. It won't work on any of the new laptops or anything like that. But an old-fashioned television screen, you get close, and you're going to see this. You're going to see red, blue, and green. And when you look at all those equally together and you back up, it actually makes white. So old TV screens and old computers, technically, there is no white on the screen. It's just these three colors mixed equally to achieve the color white. This explains it right down here. We've got blue, red, green. You put the blue, red, green together in equal proportions, and you get white. I want to show you something. Okay, here's what I wanted to show you. This is a color wheel. Notice we've got some of the primary colors of light on here, but there's also some white. But you can easily see that there's some colors on here. Let's bring it a little bit closer. But what happens if we try and mix all these colors together? Let's do that and see what happens. I don't know if this works out really well on a computer screen, but if you look at it, from my perspective, it appears white. I didn't change it. It still has the colors on it. And now you see colors again. That's just a good example of mixing all the colors together to get white. And I don't know if I paused. I just had a conversation with a colleague, so I forget where I was at. But if you haven't already, click on a link about brain pop and color. Oh, wait a second. I can't show that to you because I'd have to give you my brain pop account. Sorry, strike that. Never mind. Let's keep on moving on. Oh, by the way, I'm going to have to pause the video right now. I'm only allowed to record 15 minutes at a time. I'll put a link on this slide to guide you to my next video. So this is my first video, and follow the link to the next video, and we'll wrap this up. There's only a few more slides to go through.